Chapter 21, Magnetic Forces and Magnetic Fields. So we've spent the first 3 chapters talking about electric forces and electric fields and all the ideas that come out of those, the idea of electric potential energy, electric circuits. And now we're adding something else in the mix, something that it turns out will complement our electric fields very nicely. So we're going to take a look at the magnetic side of electricity and magnetism. The very first section here, section 21.1, is looking at magnetic fields. So we're going to start a little more abstract here and imagine a compass. You may have had one if you were ever in Scouts, right? That you could orient yourself using the compass, and the needle of the compass, that arrow in it, is just a permanent magnet that has a north magnetic pole and a south magnetic pole at the other. And that magnet's free to rotate in order to point in the direction that is north, no matter how the support is oriented. So these magnetic poles, it turns out, are actually very similar to electric charges in how they behave. If you have 2 like poles, like a north and a north pole, they're going to repel each other. Similarly, if you have 2 south poles, they're also going to repel each other. So that's like if you have 2 of the same charge, those repel each other. If you instead flip one of those magnets around so that you have a north and a south pole near each other, or a south and a north pole near each other, there's going to instead be an attractive force, just as when you had 2 opposite charges, there was an attractive force between them. And we'll get more into this force in the time to come. But for now, we want to talk a little bit more about the magnetic field and what that even looks like. And one way you can figure out what it looks like is you could take a bar magnet like this that has a north end and a south end, or poles, and you could put a whole bunch of little compasses around it. And what you'd find is that the compasses would all orient so that they're pointing out of the north and around and into the south, right? And you can remember each of these little compasses has its own north pole and south pole. So the south is drawn to the north end, the north is repelled by it, right? And so it forms this loop that can go on either side, and you'll see that there are more loops beyond, right? And this might start to be looking a little bit familiar. We've seen something like this before. We've seen this when we had 2 opposite charges, the electric dipole. So this is starting to feel very familiar in a sense. So we know that there's this magnetic field, and we can sense it using a compass. How else could we sense it? Other ways that you can show the magnetic field lines are you could put iron filings near a magnet. The pieces of iron are small enough that they're in the right material, so they're able to magnetize, to develop an end that's south and an end that's north, similar to how we had charges slightly separate. And so they form out these lines just like our electric dipole. So if we fill in all of the lines, it looks something like this, where the magnetic field lines go out of the north pole and wrap around and point into the south pole. And this is true when you have a bar magnet like so. It's also true when you have a horseshoe magnet, right? Where you just have a north on one end and a south on the other, and a gap between. Notice it's very straight in the middle. That's a sign that the magnetic field there is uniform. And then the edges are where it starts to bow. This looks a bit like our parallel plate capacitor. So some of these ideas help us to get a picture of the magnetic field, even though we typically can't see it around us. But it is something that's always there. We're in the presence of magnetic fields nonstop, including one from the Earth itself. Right? So I mentioned that with the compass, you can always know which way north is, based on how the arrow lines up? Well, that's because Earth acts very similar to a bar magnet, with a magnetic south pole up at the geographic north pole, right? So that's why your compass then lines up with the north end going up and the south end down, so that you have the like attraction. So the magnetic field lines of the Earth come out of the south pole and the geographically south pole and into the geographically north pole. So that's a fun fact there. The Earth, it turns out, actually, it's random which orientation it is, and over lots and lots of years, it slowly flips which end is north and which end is south. So if you want to know more about this, that's an area of geology. But next up for us is understanding a little bit more about what's going on with this magnetic field and how that's tied to a magnetic force. So stick around.